So today it's our pleasure to have Thore Husfeldt here, who will tell us about the shortest even cycle problem. Please, Thore.
Thank you very much. Thank you for joining either in the flesh here or online. And thank you for inviting me here. This is highly prestigious. I hope I can live up to it. The result is, I think, super accessible. So I will try to break down this presentation into two parts. One will be a almost comically accessible introduction to what the problem is and some big picture hand waving with nice animations about how this is solved. And then there will be a slight break. And then I will want to switch to the iPad to sort of test the envelope of what we can technically manage. And then try to do some of the neater proofs in detail. There are a number of details that will remain under the rug. On the other hand, the result is actually short and sweet. And I think the first 6 pages of the paper are self-contained, though dense, and establish the entire result. So I think this is certainly accessible. Okay, so it's about the shortest even cycle problem, and what I want to tell you is that it is tractable, and tractable here means that it allows a polynomial time algorithm. And to my own surprise, this was an open problem. This is joint work with Andreas Björklund, who's also here in Lund, and Petri Kaski in Finland, Aalto University. So most of my slides are super complicated and build up, and all of them, just for my own navigation, start with sort of the spoiler. So the build up that starts here, you sort of already know how that is going to end. It's going to end with this picture. So our instances will look like this. They are graphs, directed graphs. I will just say graphs from now on. They could potentially have self loops, and they will later in the construction. Think of them as not having parallel edges. Again, that's not so important, but just to think of graphs like directed graphs. And what I want to look at are cycles, and cycles, as you all know, at the danger of insulting the audience, are subgraphs that are closed and non-self-intersecting. So here's a cycle of length 3. Note in particular that the cycle has to follow the direction of the edges. So I more formally talk about non-self-intersecting directed cycles, but I will just say cycles. And non-self-intersecting directed cycles are non-self-intersecting directed closed paths. Okay, so this graph has a bunch of cycles. I took the liberty of actually identifying all of them here. And there are not that many, it's a small graph. And some of them are have an odd length. Actually, most of them have 3, 3, 3, 3, 5. Then here's one of length 6. And when I say length, I mean number of edges or number of vertices, which is the same here. Our graphs are not weighted. This I can't see 8, possibly on 7. I don't know. This has 8. Yeah, so then this one will have 7. There are 9 vertices in this graph. And so the goal of this is, given an instance such as this one, find a cycle of minimum even length. Just let's unpack that. We're not looking at the cycle of minimum length, that is this one has length 3, or this one, there are actually a bunch of them. We're also not looking for an even cycle, because there are 2 even cycles, this one of length 8 and this one of length 6, sorry. We're looking at a cycle of minimum even length. That may, in some graphs, be the shortest cycle, but then it's a very easy problem. So
you can also do odd cycles if you want.
I'm sorry?
Can you also do odd cycles?
So odd cycles, there will be a slide for that.
Yeah.
Odd cycles is a heartbreakingly easy problem that has been solved since the 50s. Okay. What is interesting here is that even cycles has not. And we will see the difference in just a moment. So the short answer is yes, but so can many people. Okay, problem is clear. Why this should be difficult should be very unclear. Okay, just for completeness, here's a different graph. Let's again start the breathtaking animation of enumerating all the cycles. This has cycles of length 3, more of 3, a bunch of 3s actually. Very regular construction, this one. And once we're done enumerating all the cycles of length 3, there are a bunch of length 5. And then there's the Hamiltonian cycle that goes through the perimeter of the graph of length 1, 2, 3, 4, 5, 6, 7. None of these cycles have even length. So there are graphs like this one that fail to have an even cycle. And in that case, of course, we don't want the algorithm to crash. We want it to correctly output that there is no even cycle. Okay, so this is the problem. Given a graph, if there are no even cycles, tell us. If there are even cycles, find one of minimum length.
And you want to report the cycle, or
so the algorithm I'm showing you just detects it. It gives us the minimum k for which there is a cycle of even length. If you then also want to see the cycle, there is what is known as an obvious self-reduction that finds this for you. And let me just convince you of that. So if I had an algorithm that would just detect that there is, so I put this in and out comes the number 6, then I could iteratively remove vertices from the graph until the number no longer. And so if I remove this vertex from the graph, then there's no longer a vertex of size 6. If I remove this vertex from the graph, then there still is a vertex of size 6. So with linearly many calls to such an oracle, I could also determine such a cycle. I guess I want to remove edges instead of vertices, because otherwise I have a multiplicity problem left. Okay, let me change my story here. With m many calls, where m is the number of edges, with m many calls to the oracle, I can even determine one.
Okay, yeah.
Since the result here is a polynomial-time algorithm for a problem for which we didn't know that such an algorithm exists, my glasses are not sharp enough to even see the difference between these two problems right now.
Good point. Thank you.
I think this is a super good question. And we don't know of a better way of doing it. So that would also be interesting to see if there was a optimization version of the problem can be solved better than just calling the decision version n times. Okay, this is where we are. And I can't remember what's on my next slide. Okay, so as I tell you, I want to tell you about the shortest even cycle problem, and there are two adjectives here. Both of them are critical for this talk being interesting, because there are these 4 obvious alternative versions of the problem. Just find a shortest cycle. I don't care about whether it's even or odd. Just find a shortest odd cycle. That was the question you asked about. Do the same problem in undirected graphs, or just find an even cycle. I don't know. I don't care about its length. These are all valid variants of the problem. They are known, and I want to talk you through them. Right, so the top line is new. This is what we do. The other ones are either easy or breakthroughs. And we can't see from the title of the problem which ones of these are super easy and which one of those are amazing breakthroughs in combinatorics and graph theory that made their authors very famous. I would just talk you through them, and it should sort of be entertaining and should be small nuggets, and you can fall asleep and wake up again during the talk. So let's do the efficient algorithm for shortest cycle first. And this allows me to introduce another thing that is going to be important for this talk. Again, at the danger of insulting the audience, to every graph G, we naturally associate the so-called adjacency matrix, which we have enumerated the vertices in an arbitrary way, and then if there is an edge from vertex 4 to vertex 8, we put 1 in row 4 and column 8. So this is the well-known adjacency matrix. And this moves a combinatorial problem into the realm of linear algebra because this is the matrix. So we can do fancy stuff with that. I will show you some very easy stuff. But the main technique that we use does just more advanced stuff like this. So basically translating a combinatorial problem into something where we can use truth from algebra. And just to give you a feeling for how this works, already the square of the adjacency matrix has a natural combinatorial interpretation. Let's just do this very slowly. There's a 1 in the square of A, because when I multiply in row 1, column 5, algebraically, because when I multiply the first row and the 5th column, then there will be a point where the pairwise products agree, and I guess it's when this one here is multiplied by this one, if you can do this vector multiplication in your head. So this will end up with a 1 in this position. So algebraically, it's clear why there's a 1 in this position. The square of A, and you can reinterpret that combinatorially. There's a path from 1 to 5, that is row 1, column 5, because you can take a detour via 2. So the 2 exactly picks out the second column here or the second row here. So the square of the adjacency matrix counts the length 2 paths. Actually, I should be careful here because it does not count the length 2 paths, it counts the length 2 walks. As we will see in a moment, let's do this just for one more iteration. The cube then counts walks of length 3, including closed walk, and a walk that starts at a vertex like 3 and goes back to the same vertex, like via 6 and 9, has an entry on the corresponding diagonal. So there's an entry in diagonal 3, 3, corresponding to vertex 3, because there's a path of length 3, sorry, a walk of length 3 that starts in 3 and via two vertices goes back to 3. So there's a natural and well-known correspondence between the walks in a graph and the powers of the adjacency matrix. Here you could take the trace of the ith power, and that has a contribution exactly if there's a walk of, for instance, length 3. And this is not going to be our solution, but our solution is going to taste like that, just spicier. Let's just do this all the way up to 6, just to see some. And the reason to do it up to 6 is because I find it slightly instructive. So I can follow the path of a 6 walk through my matrix powers here. So as I continue, more and more matrix powers become activated. And then you can see, looking at the diagonals of these matrix powers, you can see there is something at the diagonal of a to the 6, exactly because. So there is a contribution in this diagonal because there is a 6 cycle. So this sounds a bit too good to be true, and it is too good to be true because this 6 walk here, 1, 2, 3, 4, 5, 6 is also a 6 walk. It also contributes, here's its contribution in the 6th power, and it messes up the entire story because so the diagonal entries in a to the 6 have contributions from the things I want to detect, but they also have contributions from things I don't want to detect. So if I could just get rid of these self-intersecting things, then I would be in business. Of course, then P would be equal to NP because this would be an algorithm to find the Hamiltonian cycle. So I just look at a to the n and see if there's a diagonal entry. If all walks were paths, then I would have solved the Hamiltonicity problem in linear time by Gaussian elimination. No, sorry, by my matrix multiplication, because that's in P. So this doesn't work, and it cannot work for some deep reason. But again, the basic story of naively translating a combinatorial problem into a linear algebra problem is exactly what we want to do. Okay, so let me just spend a bit of time on this good question about how about the odd cycles, because that sounds very much like the same problem. So let's look at it's the same graph thrice, and I want to do 3 different things to it. In the top, first note that closed walks need not be simple. We already saw that on the last slide. So here's a closed walk that is not a simple walk, is not a simple cycle. And that means that, however, a shortest closed walk is simple, right, by definition. Otherwise, it would be partitionable into shorter closed walks. One of them has to be simple. So a shortest closed walk is simple. In general, closed walks are not simple, but shortest closed walks are sort of special. So, and this means in particular the shortest cycle problem is in P by the algorithm I just showed you. Just build the adjacency matrices until you get a contribution on the diagonal. And when you have this contribution in the diagonal, then you know that you have a closed walk. And if it's the first matrix power, then this must be a shortest cycle, not only a shortest walk. So the shortest cycle problem is in P. There are many ways to state this. right? I guess you would much more want to run breadth first search from every vertex, right? And breadth first search from every vertex and repeated matrix powering roughly is in the same ballpark of how much time you need for that. Actually, not running breadth first search from every vertex would be stupid. Of course, that's what you want to do. But unless you already have a numerical algebra bucket, I mean, if you do this in Python, then you probably just want to do that in NumPy. Okay, so just to get this out of the way, the shortest closed walk, the shortest cycle problem belongs to P, and you could be in a position where the shortest closed cycle has even length, like here, and then you would have found a shortest even cycle in polynomial time. So the interesting cases are the graphs where the shortest even cycle is not the shortest cycle. Now, moreover, by a parity argument, not only is a shortest closed walk simple, a shortest odd closed walk also must be simple. So, and here's, and it's simply because you can't add many zeros modulo 2 together 1. This is called the parity argument. I always mess this up, which is why I wrote it down here. So, but I can only understand this by example. So here is a shortest odd closed walk. It has length 5. It is not the shortest cycle in the graph. That was this one, the green one. But it does. But this thing of length 5 cannot decompose into shorter odd cycles. Right? If you have something, the parity of which is 1, then it cannot only decompose. Then it must have. Did I say this right? If you have something of parity 1, like this 5 guy here, then if it decomposes, it cannot decompose into only even cycles. There must be an even cycle into it in its components. Component is not the right word, in its biconnected components. Right? So by a slightly, more or less the same argument here, but slightly tougher, because it needs the parity argument, shortest odd closed walks are also an easy problem. Just run the iterated matrix powering algorithm. This one, 1, 2, 3, and so on until you get your first odd contribution. And then that is going to be a shortest odd cycle, even if there were earlier shortest even cycles, right? By this picture here. So the first time you get a 5 walk, you know that it's going to be a shortest odd closed cycle. So the shortest odd cycle problem also belongs to is in polynomial time. Again, you can just run breadth first search in time so that you find it. And on the other hand, so this seems to be almost an empty argument. You only understand it when you see the opposite. Shortest even closed walks need not be simple. Here's a shortest even closed walk, and it's length 10, I guess. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. So here the light blue thing is a shortest even closed walk of length 10 in the graph. It is not simple. And it does not decompose into only it. And I have just decomposed it into 2 odd cycles. So I can not decompose odd things into only even things, but I can decompose even things into only odd things. That's the difference between odd and even. Right? Because, so again, 1 is not a bunch of zeros, and 12 can be 5 and 7. And 11 can never be 8 and 4. I always mess this up. So, right. And this is sort of why odd and even are very, very different. This naive just do breadth first search or matrix multiplication does not work simply because of this fact. In fact, this graph doesn't have any even cycles at all. It only has odd cycles, right? One of length 5 and one of length 7. It has an even walk, but no even cycles. Okay, so this is my best attempt at explaining why there is a problem at all. All of this was known in the first few weeks when people started thinking about graph algorithms, right? 50s or something. And so as soon as people in the 50s started to view basic combinatorics problems through the lens of graph theory, then these insights were immediate. So this is all known before. I mean, I tried to attribute this argument to something, and I think I found a paper, and but maybe the earliest one, but it's probably old folklore. It was sort of born as folklore. Questions, comments, protests? Okay. So note that even detecting an even cycle, independently whether you want the shortest one or not, is not something that is obvious how to do that. And in fact, and this is the slide I'm most proud of, unfortunately, it's not our result, it explains a different result. But let me talk you through it. So this is so cool. So in the undirected case, this problem was solved early on in the history of algorithms. After 56, I guess the argument seems to be well known. There's a paper that refers to it as Waterloo folklore. So some people seem to know somebody at Waterloo who had this insight. And the argument goes like this. So we take our problem and consider the undirected version of it. So this is the only part of the talk where we look at the undirected graphs. So consider the undirected version of the graph, make two copies of the graph, a green one and a red one, and connect the vertices in with this matching. So construction is clear. I just took the graph twice, connected vertex U1 with vertex V1 for every vertex, for every copy of the original vertex U. No, 1. Sorry. And then you can do the following trick. So just to start the algorithm. And now I want to solve a matching problem in this resulting undirected graph. And I make the gray edges very, very tasty for the matching. So the matching wants to eat as many gray vertices as it can, and as few red and green vertices. Now, if this was the instance, then what would be the size of the matching? Yes, n, right? You can just pick all the gray edges. So let's make it slightly harder. And so here's the solution. Let's make it slightly harder and subdivide a single arbitrary edge like this one. So I take this edge and I subdivide it and put some new leaves on that. Now your solution does no longer work because if I pick all the gray edges, then these two vertices are not matched. So I have to do something else. Okay. It's also clear that the yellow vertex has to be matched with something. And I guess I should say perfect for something. Should I? No, maybe not. Doesn't make a difference, but
you want maximum weight?
I want maximum weight matching, then I could still take all the gray ones. So I guess I need a maximum weight perfect matching. Yeah. So it's quite clear that this guy has to be matched with its neighbor, and then just look at the construction. So then you go down here and pick something there. So you continue. And if you do it carefully, then you can see that there are many constraints on this. So the only thing you can do is really follow this matching here, and then finally you go back here. And now for the remaining vertices, those that have not been part of my complicated dance here, for those you can then do what we did at the beginning, maybe just pick the desirable edges. So this is a matching of size 3, and everything else is now matched with these 3 edges. Now, if I reinterpret the path I took through this construction back here, then it should be clear that as you saw, I alternated between the 2 copies, the red and the green copy. And since I alternated, I must have picked an even number of edges. So reinterpreting this construction back gives me an even cycle in this graph, after sort of now identifying these 2 vertices again. So the cycle is even, and it is minimum because I still try to pick as many of the yellow parallel edges as I could.
Okay. Minimum, supposing it contains this edge. You have to do this for every edge.
Oh, very good. Yeah, I have to run this for every. Oh, right. I could not pick this arbitrarily. I have to pick it arbitrarily on. Yeah, thank you. So this boils down to m many. Yeah, m many, where m is the number of edges, m many calls to an oracle for finding maximum weight perfect matchings or something. And there's an algorithm of Edmonds for that. Right. So this is also belongs to polynomial. So this problem does belong to polynomial time, but by appealing to one of the cleverest algorithms ever invented. Right? And it must have felt in the 50s and 60s when these algorithms were discovered that this felt like the right direction to go in. And if we could just continue doing that, then we would solve this problem as well. But it turned out to be this turned out to be a dead end. So now we go back in time. And since you're a captive audience, the door is closed. I will actually allow myself to read this out in German. Those who have no German can just admire my diction. Those who have German will find this hilarious because the construction is just amazing. So this is Polya writing in 1913 in a German journal mainly aimed at high school teachers. Die Regel für die Entwicklung einer Determinante, so the rule for developing a determinant, besteht aus zwei Teilen. Der erste Teil gibt an, welche Produkte aus den Elementen zu bilden sind, während der zweite Teil das Vorzeichen, the sign, der gebildeten Produkte bestimmt. Der zweite Teil lässt sich im Falle der zweireihigen Determinanten auf folgende Weise vereinfachen. Man ordnet diesen 4 Elementen beziehungsweise diese 4 Vorzeichen zu. Dann trete jedes Element in die durch den ersten Teil vorgeschriebenen Produkte mit dem zugeordneten festen Vorzeichen ein. And this is just amazing. In die durch den. So no, basically what he's saying is that there would be a much easier way to explain determinants if they were all 2 by 2, because we didn't need this alternating sign. We could just make as a rule that you always multiply that with a minus. And then everybody would be happy. Nun ist, and it's an exercise aimed at high school teachers and their students, nun ist nachzuweisen, dass eine entsprechende Vereinfachung bei der Determinante mit mehr als 2 Elementen unmöglich ist. Das heißt, es ist unmöglich, den n-Quadrat-Elementen n-Quadrat feste Vorzeichen derart zuzuordnen, dass, wenn die Elemente in die durch den ersten Teil der Entwicklungsregel vorgeschriebenen Produkte mit dem zugeordneten Vorzeichen eintreten, ohne weiteres das richtige Vorzeichen bei allen Produkten herauskommt. So this is really amazing. High-style German written by a Hungarian, of course, which Polya. I'm super happy with this. So let's just solve this. No, let's not solve it because there's an online audience. You can. So the question is this always true? Is there always a way to just add pluses and minuses given the numbers? So given a concrete matrix. And for 2 by 2, the answer is yes, as we just convinced us here. But for 3 by 3, the answer may not be yes. So given a concrete 3 by 3 matrix, is it possible to, once you see the numbers, to just put pluses and minuses into those numbers so that you can ignore the minus sign in the definition of the determinant, which is complicated and involves the sign of a permutation? And the answer is no. And this is a super entertaining exercise. You can just, so for completeness, look at, maybe I need some more. So just to spell this out. So at the top, you see the definition of the determinant. There's at least 3 different ways to define the determinant. Here's one. So it's a sum of all permutations times -1 for something complicated, times a product of the entries picked out by the permutation. So for a 2 by 2 matrix, it's AD minus BC. And there's a closely related product, a construction, which I would call sort of the student's determinant, which simply is annoyed by the -1 stuff and just forgets that. And that is called the permanent. So this is the permanent. It's the sum of all permutations of just the entries picked up. And then as we saw, instead of computing the determinant, you can just compute the permanent of the same matrix where I changed the bottom left entry by adding a -1. And as you can see, in this case, the determinant equals determinant. Polya's question is can this always be done? At Polya's time, the word permanent was not established. But this is basically what he asks. And if you consider, just to relieve you, if you consider the 3 by 3 all ones matrix, so the matrix 1 1 1 1 1 1 1 1 1. It has 6 entries in its sum because the permutation of 3 entries is 6, 3 times 2 times 1. Right. So if you write this out for the matrix 1 1 1 1 1 1 1 9 ones, then that contribution gives you 6 terms. The permanent, each term is a 1 for the permanent. So the permanent of that matrix is 1. The determinant, and that you have to sit down and do, is also 1. But and if you put, sorry, the determinant is not 6, right? The determinant also just consists of pluses and minus ones that are added, 6 terms, and they can't all be positive. And yeah, this has to do with every term appearing in at least 2 factors. So yeah, so the answer is no, and you can just sit down and fiddle with a 1, 1, 1, 1, 1, 1, 1, 1, 1 matrix. So the answer was no, but it's a nice algorithmic problem that has become known as Polya's problem. So let's again build this up slowly. This slide. So a problem that I tried to tell to you with anomalous Polya's problem is, given a matrix numbers, integers say, is there a way to add minus signs to some of these entries so that the determinant of the matrix equals the determinant of the matrix? Here's a yes instance, by the way. So for this particular arrangement of numbers, it can be done. If the arrangement had been 1, 1, 1, 1, 1, 1, 1, 1, it cannot be done. So it depends on the input matrix. Polya's problem for the permanent. In general, it was unclear what the answer is. And this is avant la lettre. We didn't know how to define algorithms, but today we would say, given a matrix A, determine if there are entries I can flip such that determinant equals permanent. That is an algorithmic problem. And there are some others. Let me talk you through them because this is entertaining math. Given a matrix of signs, so I just tell you that minus, plus, and 0. Is there a way to put integers consistent with these signs so that the resulting determinant is non-singular? And here the answer was yes. So given this matrix of signs, there is a way to put integers there. In fact, here it could just put ones, minus ones, and plus ones. And then you can check that if you compute the determinant, it is non-zero.
Integer or Boolean?
I think integer, but it's hard enough. Wow. I think it's hard enough even if the integers are known to be +1 and -1. I'm out of my depth here. Certainly the integer problem, so given a matrix of signs, can I put integers that are consistent with the signs so that the result is 0? That is equivalent to this problem. Right, so it was quickly seen that Polya's problem is equivalent to the non-singularity problem. So there's a way to polynomial transform this problem into that problem in the other direction. Even cuter, maybe the per equals that problem, given a matrix of, now I have to be careful. Yeah, given a matrix of zeros and ones. Yeah, given a matrix of zeros and ones, is the permanent equal to the determinant? That problem also turns out to be equivalent to this and equivalent to that. And this one we will revisit in a moment. Here's another version of the problem. Hypergraph 2 coloring. So hypergraphs are nasty to draw, but here's a well-known hypergraph called the Fresnel plane. So the edges have length 3 here. Every edge has 3 vertices on it. And the drawing should sort of make it clear to you that there's a 3 edge here, and a 3 edge here, and a 3 edge here, and a 3 edge here. And then there's the 3 edge containing the vertices. Sometimes it's drawn with a circle here, means the same thing, right? So this is a hypergraph on 1, 2, 3, 4, 5, 6, 7 vertices, and 1, 2, 3, 4, 5, 6 hyper edges. So 3 sets. And then I want to associate colors to the vertices so that every hyper edge is non-monochromatic. And here you can see I failed. There is a hyper edge that is monochromatic, an all red hyper edge. Would there be a way to distribute these colors differently so that the hypergraph has the so-called balanced 2 coloring? And for this particular instance, the answer is no. The Pfaffian orientation problem, given an undirected graph, find an orientation of the edges such that, and then you need the definition of Pfaffian, so that's just nasty, and I'm not going to repeat it here, you can look it up, has to do with how many cycles there are in one direction and how many in the other direction. And finally, the even cycle problem, given a directed graph, solve the decision problem of recognizing the existence of an even cycle. So this is a yes instance, and I have highlighted an even cycle in green. This is our slide, our friend from the first slide. As we know, there's also a shorter even cycle. That's not important right now. Just finding any even cycle is enough. So these problems and many more, 28 or so, are all polynomial time equivalent and have been studied very intensely in the 90s. In the 90s, there was a bunch of papers attacking the even cycle problem, partly inspired by the connection to Polyo's problem. And this was solved in 97, very famously, and the result, and the answer is yes, this admits a polynomial time algorithm. So there was a paper should appear in the top right, in the bottom right corner. Yes, it does. In 97, two different sets of authors, Robertson, Seymour, Thomas, and McCuaig, I don't know, who discovered in 1997 that there's a polynomial time algorithm for this. These are tour de force combinatorics, like 90-page papers using, which part of algorithm combinatorics are using? All of it. It's really, really tough going. I will not even pretend to have read those in depth. And this result then appeared in the Annals of Mathematics. So this has been extremely well received. STOC 97 and Annals of Mathematics. So I think the history lesson now ends. And I will tell you what to do about this. Overviewing-ish, and then we'll see how far we get in the questions, comments, protests. I hope you agree by now that this is a super nice problem. I will typically, from now on, look at graphs that will be slightly sloppy. Sometimes the self loops will be there, and sometimes they will not. But so algebraically, this is just a question of adding ones in the diagonal. The connection between the even cycle problem and the permanent problems is given by the fact that the permanent witnesses the existence of cycle covers. So after adding these ones on the diagonal, this is a sum over all permutations. And I've written all the permutations down here. There are 320,000 of them. So this slide is very broad. We're just seeing one of them. And a concrete permutation like this one, of the 9 vertices corresponds to a choice of edges in the original graph. And let me just talk you through this. And let me put some numbers on there. So this permutation means that 1 becomes 7, 2 becomes 3, and so on. It's a brief way of just describing a permutation. And so a concrete permutation corresponds to a concrete choice of edges in the underlying complete graph of the vertex set. So for instance, 1, 7 would be an edge from 1 to 7. And that actually exists in this graph. Clearly, I was not thinking of 1, 7 when I made this slide. Maybe I thought of 7, 8. Maybe 7, 4. So let's look at this. So 7 is mapped to 4. That corresponds to taking 7 and putting it, mapping it to 4. There's actually an edge here, and the existence of that edge should be recorded by the 1 here in the adjacency matrix. So for a concrete permutation, this part, the product of the entries in the adjacency matrix, is either a 0 or a 1. I know some of you find this super boring, but it's either a 0 or a 1, and it's a 1 exactly if all the entries picked out by the permutation actually exist in the matrix, as they do in this case. So this particular permutation, the beige orange one, corresponds to a choice of fitting entries in the adjacency matrix, all of which exist. This corresponds to edges in the graph, all of which exist. Hence, this particular permutation corresponds to a cycle cover. So the terms in the adjacency matrix correspond exactly to the cycle covers. Some of them contribute with a 1, And some of them, like this poor guy, do not contribute to a 1, for instance, because this particular permutation picks, say, 8, 2. There's a 0 here corresponding to there not being an edge from 8 to whatever to this, probably this one. Right? So this huge sum picks out exactly the cycle covers in the graph. And that's not a help at all. We've just translated a nice finite problem about a graph into computing all the terms of an expression that is exponential, actually super exponential in the size of. So this clearly goes in the wrong direction right now. It's going to be exactly the solution we're thinking of. Let's just enjoy this, because once you write that code, you might as well actually look at this. So you saw the first, that is important actually. The trivial permutation contributes. It will always contribute here. So that is the diagonal entries where I carefully put ones here. And then you get, in this case, I think 13 other contributions for all the cycle covers that exist in the graph. Right? And here all of them. One of them, I think if we are awake, it will appear quite soon. One of them is our friend. Yes, here it is. There it is. You saw it? Blink and it's gone. That was the one we want to pick out. So all that is left now is among these 320,000 terms, many of which just vanish, luckily, to pick out the one that we want. So that's our ambition now. And I just picked out a few representatives of the contributions that did not die, because I need some more terminology. Here's the green cycle cover that we're looking for, the one that has a shortest even cycle. In some sense, it appears twice. It appears with these self loops, and it also appears with this annoying 3 walk. Here's another friend of us, the even cycle of length 8. You don't want to find that. Actually, just finding it also makes us kind of happy, because we are re-establishing a completely different algorithm for the even cycle problem. So we are not sort of embarrassed by this. But what we actually, the contribution today is finding this one. But there are also a bunch of other cycle covers that we would not like to not find, like this one that has a cycle of length 5 and no even cycles at all, this one and this one. The handle that we get on those is the number of connected components. So note that the cycle covers with an even cycle in it, the number of connected components has a different parity than the number of vertices in the graph. This is most clearly seen here. So this graph has 9 vertices, so it's an odd graph if you want. So the one connected component takes away parity 0 because it is even. Right? And then there are 3 small connected components left. So the number of connected components is 4, and the number of vertices is 9. Whereas, just to build some intuition, here, of course, the number of connected components equals the number of vertices, so in particular has the same parity. And every time I move such of odd things away, then I will reduce the number of connected components by 1, that has parity 1, and I will also take away an odd number of vertices, so that also has parity 1. So these parity arguments mean that the odd things and the even things we can distinguish by just looking at the number of connected components. And now we start to be in business, because as you remember, the number of connected components actually appears in the definition of the determinant permanent. So this will be our first goal. And let's do this slowly.
Sorry, are
yes.
you, so when you say that the number of components, you mean when there is only one even cycle? Like if you have 2 even cycles, then you're putting it in the odd case. You have an even number of even cycles.
What you say is correct. So that's why we have to be slightly more careful. And if we get to the second part, I will be super careful. So yeah, it's useful to currently think of these cases where everything else is in these stealth loops, because then your correct counter argument is not applied. So this is under the rug. You are not supposed to see this. Here's our graph, the adjacency matrix, and the definition of the permanent. And here's the definition of the determinant. It's almost the same thing, except the permanent, the determinant is sort of can see these connected components. This may not be the definition of the sign of a permutation that you remember, but it is an equivalent thing. So signs of permutations can be defined in many different ways, and one of them is actually the number of connected components or orbits or whatever it is. And let's look at two instructive graphs. The one that contains an even cycle and a bunch of self-loops. So that contributes just a 1 here, as it's, there's nothing fancy here, so this just contributes 1. In the determinant, it contributes negatively, right? -4 is 5, so -1 to the 5 is a negative number. Whereas this guy with a 5 cycle contributes positively to the permanent and also positively to the determinant. Something is wrong here. No, it's not. 9 - 5. Right? So in particular, if I add these two things, or sorry, subtract them, if I subtract the determinant from the permanent, then the green contribution, then the green cycle contributes twice, and the red cycles just disappear. And this is the first argument. This is a cancellation argument. The first argument that plays an important role for us. So the fundamental structure that we're going to investigate is the difference between the permanent and the determinant on the adjacency matrix, because that is still a thing that has an exponential number of terms, but the only contributions are even cycles. And now you can also see this was one of the equivalent formulations. If the permanent and the determinant are equal, then this is a 0, and hence all of these have disappeared. If the permanent and the determinant are different from 0, there must be something. In particular, there must be an even cycle. So this gives you a proof for free that the even cycle problem is equivalent to computing permanents and determinants for the same matrix. None of this helps because this is famously a number p-hard problem. I'm just re-expressing a problem that looks very, very difficult in a problem that I know is very difficult. Okay, so this is the Vazirani-Anakakis result from 1989 that per minus det is morally equivalent to the even cycle, and which is algorithmically not interesting because per minus det is a number p-hard problem to compute. And this is, I think, most better people would just give up here now, but now it comes. So I will not, instead of looking at the, seems to be a slide missing. Oh no, it's not. It's not missing. It's just complicated build-up slide. Sorry. Okay, so now comes the trick. Well, one of the tricks. Look at the adjacency matrix of the graph without self-loops and add the identity matrix with a formal variable y glued onto the diagonal. Now, so this now is, so this is a polynomial, a very simple polynomial, y to the 1 with coefficient 1. And so this thing now lives in the space of n by n matrices of polynomials. And a specific cycle now picks out, I have to train myself into pressing F and not space when I do these things. I'm sorry. So a specific cycle, like the yellow one here, again corresponds to a specific choice of picking elements either from the diagonal or that correspond to edges. The new thing is now that the self-loops now are contributions of my single variable y. So a specific cycle picks out something that now looks a bit more like a polynomial, namely 1 times 1 times 1 times 1 times y times 1 times 1 times 1, twice because of the cancellation argument. Another cycle like this one that picks no self loops is this unit polynomial. And the things we're looking for, this one, which if I had a better person was still green, it's purple, picks out many of these y's. So writing now the permanent minus the determinant of my new matrix is now a polynomial, still has exponentially many terms, but now it's a small graph, so I can actually show you all the terms. So the terms remaining are only the terms where there is an even cycle in there, modulo your correct observation. But the one with the highest power will be the one corresponding to an even cycle with many self loops on it. That will then be the shortest even cycle, a shortest even cycle. So this is what we want to compute. The per minus that of a polynomial, sorry, of a ring, of a matrix of polynomials. Okay, so that will be our mission. This. And again, this would, I think, be a completely valid place to give up, because obviously this can't be done because this is a number p hard problem. Particularly, it's number p hard in most of the algebraic structures that we want to do helpful algebra in, like rings, sorry, like fields. Anyway, I've now reduced the find the shortest even cycle problem to the find the highest non-zero coefficient of a specific polynomial in a single value. And this is the polynomial. Okay, and we will do this, and now starts the algorithmic number theory part. This is super cute, and I've slides that are very pretty, and it's not very scary. But let me just finish the argument for you. So right now, just accept this can be done, and it's not as scary as you might want it to be, or fear it to be. And there are pretty slides that do this, and that will allow us to go through this. These things put down by Valiant in 79, namely that the permanent is hard for number p. It is easy modulo 2. This is what we know about the permanent from Valiant. So, and I think these first two lines should be in the toolbox of most of you. Permanent in general is a difficult problem. Modulo 2, it's an easy problem because by definition of the permanent of the determinant, the -1 to the something goes away, because if you're modulo 2, then -1 is the same as 1. Hence, the permanent and the determinant must be the same. So modulo 2, it's easy, but of course that doesn't help us because we tried to compute. Oh, the 2's have gone. Because there's a 2 in front of it. Right? We are exactly trying to compute something that is even, and modulo 2, that's 0. So again, your intuition should tell you this is a fool's errand, and I will just show you that it actually will work out. And I will talk you through these things after the break. But just to sum this all up, to give you a feeling of which direction the argument is going. So the full overview of the algorithm is as follows. We start with our graph and the adjacency matrix, and we now translate the entries here, which are 0s and 1s, into entries in a specific ring. And I will tell you what the ring is. I showed you very briefly on a slide. I will draw these entries as these binary numbers. And there is a number in this ring corresponding to 0, and I will draw that as 0, 0, 0. And there is an entry in the ring corresponding to 1, and I will draw that as 0, 0, 1. But there are many other entries. So once we translated this adjacency matrix into a matrix over a specific well-chosen ring, we then run our new algorithm for computing. Then we do polynomial interpolation. I put a number on the diagonal. Remember, this is all a polynomial in y. I will now replace the value of y with a specific number from my ring. I will now compute the determinant and the permanent, determinant is easy, permanent is not so easy, of this matrix. That magic happens here. So there's a computation here, which I will yada yada. Out comes a number 111. Right. So I have now found out that the value of my polynomial on the red entry is the purple entry, which is just some number in the ring. And I will do that for a bunch of entries. And like the green entry, that also gives me, after some magic, it's not magic, I will show you, gives me the yellow entry, and so on. The orange entry will give me yet another point. Now the magic happens because the ring I'm doing my computations in stands in correspondence with a field that we also identified. So the ring and the field allow us to, at the right moment, do some computations in the ring, maybe computing these permanents and determinants, reinterpreting these values in a field, plotting them into a finite field. The finite field allows me to interpolate the polynomial through the points that I just picked. So, as you will appreciate, the polynomial we're looking for has limited degree. It cannot have degree higher than n, the number of self-loops. So doing this n many times, I can use polynomial interpolation to recover the coefficients of the polynomial. And then once I have recovered these coefficients, I can just look at the largest one, 3 in this case, and subtract that from the number of vertices in the graph, 9 in this case, to get 6. Hence, I know that there is a path of length 6. That's it. All the magic here happens in these equality symbols, or the magic that is left happens in these equality symbols, because it is by no means clear that I can compute permanent minus determinant of anything efficiently. And then there's some yada yada that I can then reinterpret these values in a ring as values in a field, so that I can interpolate the polynomial, which, as you remember in its definition, had exponentially many terms, but since it has small degree, cannot have too many different coefficients. 5-minute break, and then the yummy part. Or how does this work? Questions, comments, protests at this point?
I think questions first, and then maybe a 10-minute break.
Excellent.
And
Yes.
then we can.
Yep.
Any questions, comments?
Yeah.
So like the finite field, I guess you're dividing by some like big primitive polynomial.
It's not so big, but yeah.
Okay, so but like shouldn't it need to be higher than the number of vertices in your graph?
The degree will be something like log n. And I need that to be, so 2 to the log n has to be larger than 5. I think it's 5 log n. Yeah. So it's not so big.
So the ring is finite characteristic.
4. Yeah. Here we encourage characteristic 4. And we need that to be able to see the difference between 0 and 2.
You are already sure that the difference is only like 0 or 2. For example, if the highest coefficient is 8, then you calculate the 8 tells you about that.
The highest power may be 8. The coefficient, I hope, is not 8, because then I would be dead. I would never be able to see the difference between 8 and anything else. Maybe one tiny comment. Another thing that is swept under the rug here is I'm pretending there is only a single even cycle. So what I've showed you here solves the unique problem. Find the shortest even cycle provided it is unique. Because as soon as there are 2, then they would contribute twice. And 2 by 2 is 4. And again, that would vanish in characteristic 4. So there are some standard tricks, which I'm also magicking away in this presentation, of getting from the unique problem to the general problem. That is, however, well known. There are at least 2 tricks on how to do that. One uses, again, some polynomial identity testing, which I guess you've seen many times before in this context already. That's how we do it in the paper. The other way of doing it would be to use the isolation lemma. So the isolate, and I guess that is tutor to explain. If there were many shortest even cycles, I could still uniqueify them by subdividing edges with some randomly chosen vertices. And then praying to the gods that that this sort of then gives me a unique even cycle of minimum length.
So this is a randomized algorithm.
This is
By tractable, I mean randomized polynomial.
very good.
Yeah.
In general, our algorithm is a randomized polynomial time algorithm. We don't point that out in the paper, but I'm quite sure actually for the unique case, it's a polynomial time algorithm. But then you have to actually fix several small things, which I tried to convince myself yesterday are actually fixable. So we are among friends here, and nobody is going to. Yeah, I think the unique case allows a polynomial time algorithm. We have no idea how to solve this in polynomial time, and I think neither does anybody else. So this uses at least 2 or 3 really very randomized things that boil down to polynomial identity testing. I think so I think this approach will not give you a polynomial time algorithm unless there are really big breakthroughs in polynomial identity testing, which I don't believe in. Yeah, exactly. Tractable means randomized polynomial time. Very good.
Any other questions or comments? Then let's thank Thore.
Thank you so much for coming. 10-minute break, and then we will reconvene.
Yes.
Excellent.
Now.
So welcome back. For the second half, I just want to give you some big picture, what should we call this, appetizers for some of the more technical stuff in the paper. And basically that's it. I can't see myself talking for much more than half an hour. I'm also a bit under the weather, but I'm quite happy with the rest of the presentation, but it's much more local and it's much more technical, and there's no reason to understand how this all fits into the big picture. These are just 2 tiny nuggets that you can take away with you. So we will operate in 2. Our starting point will be 2 well-known algebraic objects. One is GF2, the Galois field of size 2, sometimes written as Z modulo 2Z. So that is just the numbers 0 and 1 with the obvious addition and multiplication. This is a field, multiplication and addition of inverses. And the other one is Z modulo Z4, which is not a field. These are the integers modulo 4. But this is too weak for us. We need something more complicated. And the more complicated stuff that we need is this. And this looks scary. And my whole ambition for the next 5 minutes is to sort of remove your fear of finite fields. So what we're looking at is the Galois field and the number of elements is then the middle is 2 to the 5 log 2, and that's what we're going to. That is what we will need. And this is constructed. This is a standard construction, and it's constructed by as the ring of polynomials, and monovariate polynomials. So polynomials with a single variable called x. The coefficients are from Z2, so the coefficients are 0 or 1. And then the scary part is that we divide out a irreducible polynomial G. And yeah, I don't know. Let's be very concrete because that's so much easier to understand. So let me go back in time a bit. So G, the G thing appearing here is a polynomial of the of degree, the logarithm of the number of elements we need in our field, and it is irreducible over Z2. And let's just look at a concrete polynomial to see what that is. So here's GF8. This is standard construction for a field of size 8, the finite field of size 8, called the Galois field of size 8. And we will normally that is realized as polynomials modulo this specific other polynomial. So this is just a polynomial as like you know and love, x cubed plus x plus 1. It is irreducible, so it does not factor over Z2. So there are no other polynomials which you can multiply with each other and arrive at this polynomial. Just a factoid. irreducible polynomials are quite plentiful. There are a bunch of them, basically for every size you need. There is such an irreducible polynomial, and there is a well-known randomized algorithm that finds them for you in time polynomial in the degree size. So there's standard facts from algebraic number theory, algorithmic number theory, that tell you that irreducible polynomials are easy to find in polynomial randomized time, just by picking one, checking is this irreducible, and if so, keeping it, otherwise continue. Our fields are so small that I think we don't even need that kind of stuff. I think we can easily find them by just exhaustive search, but that's not important. Just take a for a fact that something like x cubed plus x plus 1 can be found. And now, so the elements of GF8 are here. They are 8 polynomials, or rather, they are represented by 8 different polynomials. And why is it 8? Because 2 to the 3 is 8. So just to be sure, the 0 polynomial, which I will just write as 0, the 1 polynomial, which is the constant 1, and then more exciting polynomials like x squared plus x plus 1. So these are the 8 things that live in GF8. And I will just abbreviate them as the coefficients of their powers. So 0, I will identify as 0, 0, 0, and x squared plus x plus 1, I will write as 1, 1, 1. And then just because this gets really, really hard and boring, I will identify these values with colors. And so how does computation work? Computation works as it always has done, by just using the standard rules for polynomial multiplication. So if I want to multiply a specific value, like the yellow value, so yellow is 0, 1, 1, or x plus 1. If I want to multiply that with something else, like purple.
You're adding.
Am I adding? I'm adding. I want to convince us that that yellow plus purple is red. Yeah, I seem to be adding here, and there also seem to be parentheses missing. But then it's correct. Okay, thank you very much. So the white dot should be a plus sign, and there should be, and then I don't need the parentheses around the. Maybe it turns out, maybe it turns into a plus if I wait a bit more. No, it doesn't. This is just a mistake. Thank you. So, and these are just the standard rules. So adding this polynomial to the other polynomial, the x squared survives. There are 2 x's and there's a 1. Now it turns out that x squared plus 2x plus 1 in Z2, because the coefficients are taken from Z2, the 2 here is the same as 0, so this disappears. So the sum of these 2 values is the red value. And what does this, can't remember what the point of this matrix was. It was to tell us that, as you can see, no matter if I add an element with itself, then it turns blue, and blue is 0. So this is an algebraic object of characteristic 2. Adding something to yourself gives you the 0. So that was the point of this table. More exciting, here I'm actually multiplying. So let me multiply orange with yellow. So orange is, or whatever that color is, and yellow multiplied with each other gives us x cubed plus x squared using the standard rules. And now we are always promising ourselves that as soon as we have we divide it by x cubed plus x plus 1. I've done that using long division algorithm for polynomial division. And out came the purple polynomial here. So that is, and once I do this division often enough, I will certainly end up with one of my 8 members again. I can look it up, it's purple. So the product of these 2 things is just another polynomial modulus. All these computations are just built into many algebra packages. This is exactly how you realize the Galois field of size 8. I said field. Why do I know it's a field? I know it's a field because every one of these rows is nicely multicolored. So I can always get back to, in particular, every row has the mauve, the cyan in it. Right? So for every element, there's something else I can multiply it with to get one. So it's a field. So by virtue of the fact that there's a blue diagonal, and by virtue of the fact that light blue appears in every of the rows, this is a field of characteristic 2. And there's no magic involved with these finite fields. It's just polynomial algebra like you learned in school. It's a field, it has characteristic 2, so we're not going to find interesting, they're not going to help, it's not going to help us compute our favorite polynomial. But what we will do from here is extend this field to the obvious so-called field extension by interpreting the values 0, 1 as values from Z4. So 0 is just 0, 1 is just 1. But in this thing, there are more exciting coefficients like 2 or got to be 3. So this has this algebraic object, which is polynomials in one variable with coefficients from 0, 1, 2, 3, divided out by the same polynomial that we just had here. Again, if there are too many algebraists in the room, of course, I need to do some careful definitionary work so that I can understand this polynomial, which lives in GF2, as something that lives in this other field. Right? There are some ring homomorphisms that you need to define to make this all make sense, but it's just really nothing is going. It's just banal formalisms. So there's a natural way of understanding these 8 objects as just 8 objects in this much, much larger algebraic structure, which has many more exciting elements. This thing, then I could, if I made the same slide as I just did, you can quickly convince yourself that it has characteristic 4. That's not so hard. So adding something to yourself, adding yourself to yourself 4 times gives you 0, but it is not a field. It can't be a field. It has the wrong characteristic. It's a ring. So there's an obvious way of mapping values from this field into this ring. I've shown it to you here. There's a less obvious value of understanding elements in the ring as elements in the field, and that obvious way is, of course, just for interpreting. For instance, 2, 1, 1 will be this guy here. I take the coefficients and do the obvious modulo 2 operation on them. Right, 1, 3, 0 is going to be this guy. I'm losing information when I go from to that. But crucially, yeah. I'm sorry, I should divide by 2, should not do modulo 2. Dividing it. Okay, and just to convince you that more interesting things are going on. Just this is a banality, but I can take 2 of these elements and multiply them together, and then I get something that does not exist in the original. Okay. 3 is not 1, and 2 is not 0. But I will reinterpret these polynomials back into. So there's a lift in this direction and a project in that direction, and they do what they should do. And this is all nicely spelled out in the paper. And yeah, and this gives us the sort of algebraic summary. We have a field and a ring, and they communicate in exactly the way we need. And we will jump between them in the middle of algebra. I'm not going to show you these details; they are quite dry, but you just have to take it on my authority that this works. In particular, we can compute the permanent. I will show you in a minute. And here we can interpolate. And if you remember the big picture, we needed to compute the permanent, and then after that, we need to reinterpret the values from the permanent as a field element so that we can interpolate.
I don't know if it's important, but it seems from your example that you were taking mod 2 to go from the larger ring to the smaller ring. But the table didn't seem to be consistent with that.
I think maybe I'm also at the outer envelope of what I can draw without lying too much. There's a bit of lying, but I think that part was not. Oh, at the bottom. This thing?
Yeah, exactly that.
Yeah.
The one that managed to.
Let's see. Then I need to just press F really quickly. Let's see. This is the project. No, this is fine.
And you're simply taking all coefficients mod.
Yeah. And then lift inverts project and the other way around. I think that's a valid comment. There is more to be said, but it's really you have to really define just the fact that you have to define this carefully, and we do that in the paper rather.
Okay.
Just to get the computing and the permanent stuff out of the way. So as I said, what you should all know is the first two lines of these dogmas, which is that the permanent is hard for number p. In general, it's easy to modulo 2, but for all other fields it's hard. And that is less well known. It's also easy modulo 4, and that is basically the core of our algorithm. So let me just tell you how Valiant's algorithm works modulo 4. So on the integers modulo 4. So if the matrix is a matrix of 0 entries 0, 1, 2, 3, we just want to compute the permanent modulo 4. This can be done in without time. And the reason for me to want to tell you is basically just because I think I have pretty slides for that. Also, I think it's worth it. Let's see. Let me get this started again. So I have a permanent of values here. There are many different values. In a moment, we could drop down to the case where there are just 4 values. But so remember that the permanent is a sum of all permutations. And what I want to understand right now is how the permanent behaves with elementary row operations as you used to from the linear algebra class. So what happens when I take a row and add a multiple of that row to another row? Right, so I take my matrix here, take a row 4 and add row 1 to it. Right, so I took row 4 and added row 1 to it. That changed the values in row 4. Did not change the values in row 1. By just sitting down with the definition of the permanent, the same happens for the determinant, by the way. It will turn out that this gives you, so the permanent of a matrix can be expressed as the permanent of another matrix where the 4th row has changed its values, plus some error term. And the error term will have the feature that the 4th row and the 1st row are the same. In linear algebra class, where the same identity is true for the determinant, this was why Gaussian elimination works. Because in the determinant of a matrix with 2 equal rows is famously 0. So this error term just disappeared. In the determinant, and that's exactly, and that is sort of that is what the -1 symbol in the determinant does for you. It exactly ensures that the contributions of these two things eat each other, and this just disappears. And you can now just iteratively express the determinant in terms of other matrices, manipulating these matrices strategically so as to build a triangular matrix. And once you have an upper triangular matrix, then determinant is easy to compute. That is the idea of computing determinants by hand. Same algorithm does work for the permanent, except these error terms are still here, but the permanent of such a thing is not 0. Because there are no minuses. This is exactly what makes the permanent hard. But even though it's not 0, so the permanent is a sum of all permutations. Let's just take out 2 of these contributions, like these 2. So there are many, many, many terms here. I pick out a few of them. There are a bunch of permutations that will pick this element from this row and that element from that row, and then they do other things with all the other rows. I don't care. Later on, there will also be permutations that pick this element from this row and that element from that row, and then they do all kinds of other stuff. The point is that the contribution of all these terms and the contribution of all these terms are the same. Right, because this element and this element have the same value, because row 1 equals row 4. So in the determinant case, this was over 0. I don't have that luxury here, but at least I know it's an even number. Each of these stands in one-to-one correspondence to each of these. So for every way of picking something from these remaining colors, there is a way over here picking exactly the same number. So the terms in the exponential number, in the exponential expansion of the permanent, will consist of a bunch of even numbers. So I know I can express the permanent in terms of a different permanent plus something that is even. And that basically means that I know what the last bit in the answer is. It's a 0. I got 1 bit for free. So this is an easier permanent problem than this is. In the determinant world, it was even more drastic. Like this was a trivial problem. The number was 0. Now the problem has sort of dropped 1 dimension, or whatever you want to call it. I got 1 bit for free out of it. So the row expansion of the permanent formula is just the permanent of a matrix plus the permanent, it equals the permanent of another matrix plus an even number. Hence, I can, if I am in Z4, then this is something in Z4. This is also something in Z4, and this I might as well compute in Z2 because I can ignore the least significant bits. And computation Z2. Permanent computation Z2 are easy because the permanent equals the determinant. Okay, very hand wavy, but otherwise you just have to sit down and write it out, which is easy but not very satisfying to see. Okay, so the algorithm for the permanent is really the same as for the determinant. We one by one try to make the I think I'm adding, actually the computation is actually performed here. I'm quite proud of this animation. I think brown is 0. So I started here. This was my start, and then now I always add a certain row to another row that slowly changes this matrix. The values are 0, 1, 2, 3, 4. And the zeros are this dark gray number. So after at most a polynomial number of these row operations, elementary row operations, I've produced myself a polynomial number of permanent problems that I might as well solve as determinant problems. Right, so I get n squared many determinant problems, each of which I can solve in polynomial time. Now this was in Z4 and not in the polynomial ring Z4x divided by an irreducible polynomial, but with just slightly more work that still works. Right, the point is really that each of the elementary row operations reduces the number of significant bits by 1 at the expense of some polynomial factors.
And then we want to make sure that this your mapping back from Z4 to Z2 will make sure that like when you do the computations in Z2, you get exactly what you want.
That is the iffy part, and that really needs a careful proof, and it's just for him to watch me do it. But that's very carefully laid out of the paper. Yeah, right. In the end, there's just a single permanent depth, and that is just the product of the diagonal entries, as we know from the as we know from. There's only one permutation that picks non-zero elements here, and that is the inverse identity permutation. So that's why this works, and basically the main technical contribution is to translate Valiant's algorithm for the permanent mod 4 to the permanent in our ring extension of GF8. Yeah. That's all she wrote. Should we just very briefly let me connect with my iPad to this presentation?
So I'm sorry,
Yes.
I think I got lost somewhere. So all of these small examples here, they have repeated rows.
Yes, they exactly. Yeah,
Yeah.
they should have. Yeah.
Uh-huh.
Yeah. Here, for instance. Yeah.
And
Here.
then what did you say that now how are you going to compute the permanent of these?
Basically, by shifting all my values one to the right. I know that the last significant bit is going to be a 0. I know that the result is 0.
Yes.
So I will just divide by 2. Yeah, you can't really say that, but by shift everything to 2, so the bits to the right fall off, and then I have a problem in characteristic 2, and in characteristic 2 I'm fine.
Okay. Okay.
Yeah, it's just as fast to write this down on the blackboard. It's just more boring. Yeah, I wouldn't trust this either, but
Okay.
yeah. So for my final trick, I hope that I am sharing my iPad. Like now.
Yes.
Works. And I wrote down in impeccable handwriting the entire algorithm, just with slightly more detail than what you've saw. So, and this is now very close to what is in the paper, even with the same notation. So we are given a graph with n vertices, it's directed. And the algorithm starts by choosing the degree of the resulting algebraic structure as 5 times the logarithm of n. And then I pick a polynomial called G2. I would like to point to the slides, but I think there's too much lag for this to make sense.
You can point on the screen.
Let me point to the screen, yeah. Right, so I pick this irreducible polynomial G2, which is an irreducible polynomial in the ring of polynomials with coefficients from Z2. And this is done by this very simple algorithm. It just says pick one at random, and if it turns out to be irreducible, that requires a computation, then keep it, otherwise repeat. And this algorithm will terminate quite quickly. I'm not even sure we need that, but this is again a standard construction. So, and then construct the field that we call F subscript 2 to the D as the ring of polynomials in monovariate polynomials of dividing out this irreducible polynomial. So that gives us the algebraic structure normally known as GF2 to the D. Now I pick a bunch of ring elements, gamma 0, gamma 1 up to gamma n. Sorry, a bunch of field elements. So I pick n plus 1 field elements arbitrarily and distinct. Think of them as 0, 1, 2, 3 up to n. For each of these gammas,
This looks like delta.
define a matrix, which here I drew in red because I like that notation more. It's the adjacency matrix of the input graph G plus gamma L times the identity matrix. So it's the adjacency matrix with gamma L's on the diagonal, spelled out here. That if you are equals V, it's gamma L, otherwise it's just what you expect in the adjacency matrix. So that gives me n plus 1 different matrices called A subscript gamma L. And for each of these, I compute the permanent minus the determinant of A gamma L, called in our paper the parity cycle. Okay, it has a really cute name in our paper. And so I do this computation, and this is basically where the magic happens. Out of the magic comes a value delta L, which is also a member in F2 to the D. Given these pairs of values, gamma L, delta L, I will now interpolate a polynomial Q. So Q is a member of the polynomial ring with coefficients from F to the 2D. And there are a bunch of ways of doing that. Quite concretely, here is one way of doing that. So Q is simply defined as this thing here, which you may have, this is Lagrange interpolation, which you may have seen before, works in any field. I need to be able to divide. So down here is why we need a field. So this compact thing, this has n squared many elements, is a polynomial in the single variable y. And you can quickly check that it satisfies that the value of Q on gamma L equals delta L, simply by construction. This is Lagrange interpolation. Right? These almost always disappear, except if gamma L equals delta, sorry, if gamma L equals delta J, then it does not disappear, and then it gives, this is just a 1, and then the result is delta L, as we want it to be. So polynomial time, the Lagrange interpolation in a finite field, this is again well known. So that gives us a polynomial Q. That polynomial we now can just connect, and this has now n squared many coefficients. We can collect them, giving us the polynomial Q. Oh, now observe that since Q satisfies that Q on gamma L equals delta L, and PCC also satisfies that gamma L equals delta L, taken on gamma L equals delta L, and they both are polynomials of degree D, and they agree on n plus 1 points, they must be the same polynomial. So Q must equal the polynomial we're hunting for. So now collect coefficients in Q and just look at the largest one that is not 0. And that is going to be the length of your cycle. So that's it. If you want to do it for the non-unique case, it's somewhat messier, but not really much messier. But yeah, you need an even more complicated algebraic structure to begin. Here ended the sermon.
Do you want to say anything more about the non-unique case, or just it's more complicated?
So there are two ways of doing it. One would be, as I said, subdividing the vertices on any path. So randomly, by putting randomly many vertices in that blows up the graph.
But
Polynomial.
Making sure that every edge is now an odd length path, I guess.
Yeah. So subdividing every path into an odd length path. Now the even cycles are still even, but it would be very unlikely if two of them now have the same length. But this is called the isolation lemma. This is a standard trick in this field where you can uniqueify something where you, well, otherwise cancellation makes you crazy.
Then,
Otherwise, the other trick, and that's what we actually do in the paper, is to not write ones here, but to write beta UVs, where beta UVs are basically values in a, so the entire thing is not actually going to run in the, it's actually going to run, we're going to compute on polynomials. Yeah, there's no brief way of saying it. It's based on multivariate polynomial interpolation.
Okay, I should think of the betas as variables.
Yes, yeah, exactly. The betas you should think of something that I have actually plugged in already, but I'm actually thinking of computing in n by n variate polynomials, or m variate polynomials. That's the way of saying it. I actually think, yeah, I actually pretend that I'm in a, yeah, all my ones are now no longer ones, they're products of polynomials, and these no longer cancel because adding two polynomials will give you a non-zero polynomial, unless you're very unlucky and pick the values where they disagree. So this is super interesting, but standard, and it's just very tedious to explain well, I think.
in the subdividing case, can't it happen that you find a cycle that in the original graph
Yes.
was longer than the
Yes.
first one?
Oh, you have to be careful what the length. You have to make sure that you subdivide the paths you subdivide with are sort of long enough that you can, that the different things now become, that different things can have different lengths, but short enough so that you're not passing.
Okay.
Yeah, you have to be done. You have to choose these values carefully. But you have to make everything really a lot longer. So for starters, you have to make everything really a lot longer so that then the window of variance on each path does not suddenly make a short path look longer.
How do you handle this practically?
You don't.
Yeah,
I mean, yeah. I have no idea.
Okay.
But again, show me a practical instance before I think about.
Okay.
Yeah. So many of these things are just extremely. I mean, many of the tools here exist in algebra packets. There are very rich libraries for doing computations of finite fields. But the main reason to not worry about practicality right now is that this is an entirely internally motivated problem that is interesting only because we couldn't solve it. I think. But who knows? Right? Yeah. When I found the shortest path algorithm, there also were no obvious applications. And now it's in my mom's phone. I'm happy to answer more, but it's socially acceptable to just.
Any more questions, comments?
So let me just
Protests?
No, there are no protests. Of course, let me end with an advertisement. It's really writing these things down briefly and clearly just takes 5 or 6 pages, and the paper is really of such a nature that even with the blue stuff, we are done on page 9. So the entire algorithm is presented on page 9, assuming algorithms for computation in finite fields.
Do you think the field is closed now, or what is the next unsolvable problem in this area?
I don't think we know how to find an odd length path that does not have length 3 or something. I tried to look at that once, but my head always explodes. It's really weird. I think we can sort of the next shortest path. These kinds of things are really hard to find.
Okay.
And I even find, I think,
But
shortest.
to find the next, can't you take off one branch of the path you have found and then solve the problem for that?
But that's not necessarily a cycle. There's a path.
Oh, I see.
cycle.
Okay.
Yeah,
Okay.
cycle. Paths and cycles are very different. Yeah. No, there are still plenty of problems left. What I would like now here was to investigate this technique more. The running times are, if you do it with slightly more care than what I've presented here, are n to the 2 plus omega. Omega is the exponent of matrix multiplication, so it's n to the 5 among friends. I think it will be difficult to get below n to the omega. We have some developments in the paper for more graphs with more structure, or planar graphs, for instance. As soon as the graph is planar, then the matrices, the parts of the matrix interact in interesting ways. And then there are very clever algorithms that compute determinants faster for matrices that are the adjacency matrices for graphs with a lot of structure. And yeah, and there's probably more to be explored here. Otherwise, this seems to be just this. Yeah, this was not obvious to us. It's also not the result of looking for how to solve this problem, but it's more the result of looking for how to apply a set of techniques that we developed for other problems. But I'm super happy to be on the list of authors for this result.
Okay, thank you so much.
Thanks for coming.